All right, so congruent triangles. This section um, basically teaches two new shortcuts um, that allow you to see if the two triangles or if two triangles are congruent. You see here this SSS and SAS thing. These are just short abbreviations for the new rules you're going to learn. So congruent triangles, SSS and SAS. So here I have two triangles. And in the past section, or the previous section, what you had to do, you had to look at all the corresponding parts to see if they're congruent. Remember CP, CTC, corresponding parts of congruent triangles are congruent. So you look at every side, match it up with its corresponding side. Every angle, match it up with its corresponding angle, and everything needed to have the appropriate congruent marks like this, right? Absolutely every side, every angle needed to match up, and so on and so on, like this. However, this section teaches us a way to prove congruency without anywhere near that much work. We can just look at the triangles, look for a few things, and know for a fact that they're congruent. So we don't have to look at all the corresponding parts anymore if we have the right information. The first rule, SSS, stands for side, side, side. Side, 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 SSS. What it means is if you have two triangles and their corresponding sides are congruent, then they are congruent as well. So again, if the corresponding sides are congruent, then the triangles are congruent. So in this example here, you don't know anything about that angle, that angle, that angle. You don't know anything about any of the angles, but that's okay. Because when three sides are the same in both triangles, all the angles are the same as well. You did this in class. You put three pens or pencils on a desk, and you couldn't make two different triangles because if you have the same length sides, you could only make one triangle. Yeah, maybe it's flipped around, it's turned over, but it's going to give you one type of triangle. So how do you know these two triangles are congruent? By SSS, side, side, side. That's how you would answer that question. How do you know they're congruent? SSS. Just by looking at the three corresponding and congruent sides, I know that the triangles are congruent. And so then you could write a congruent statement like triangle ABC is congruent to triangle XYZ. Now let's look at the other rule. We call it SAS, which stands for side angle. Oh, I'm writing it out again. It stands for side angle side. This one is a little more difficult than the first one, side, side, side. But again, all we're doing is it's a shortcut to prove congruency. You don't need to know all the angles and all the sides anymore. You just need to know a few different things, and in this case, two sides and an angle. But where the angle is really matters. So let me show you what I mean. So if I have these two angles congruent, sorry, these two sides congruent, and these two sides congruent, right? They're corresponding congruent sides. This angle here is what's called an included angle. I'm going to fix that up really quick. It's an included angle because if you see here, it's at the vertex of these two sides, right? It's as if these two sides make a V and that angle is kind of right in the middle. This is an included angle. The angle needs to be included. It needs to be in between the two sides in question. That's why it's side, angle, side. It needs to go SAS. Order does matter. So it needs to go side, angle, side. Side, angle, side. So in this case, yes, these two triangles are congruent, mainly because, and try to follow this, if I have this length here, and this particular angle, and this length here, there is only one Imagine this side was missing. Imagine side BC was missing. Well, there's only one length of line that can possibly go from this point to this point, right? Let's say this was like a 10-inch line. Well, only a specific 10-inch line is going to fit there because this angle is like locks it in place. If this angle changes and this line comes down here a little further, then yeah, it's going to be a different length line. But since the angle is noted here in both cases, it's the same angle, that means this distance is the same, which means the triangles are congruent. That's why you don't need all the information. That's why this shortcut works. All you need is a side, an included angle, and a side, and of course, you need that on two triangles. You need them to be corresponding and congruent, and the angles to be included. Let me modify this drawing to show you what wouldn't work. So here I have a side, angle, and a side. I have a corresponding congruent side, corresponding congruent side. But if this angle over here was marked as congruent, and maybe it is congruent to this angle, maybe A is congruent to Z, well, this does not prove anything. This does not prove congruency because this angle over here is not included, right? To be included, it must be in between the two sides, and it is not. But if I go backward, let me see here. If I put it like this, again, this does work. Side, angle, side, side, angle, side. And then I can write my congruence statement. Triangle ABC is congruent to triangle X, Y, Z. All right, that's it.